was that?
Okay, 2:15. 1.3, evaluating limits analytically. So we're not going to have, we're going to try not to use a graph. We're going to try not to use a table. That is the last method we want to use. It's not very efficient, is it? You guys learned that from your homework last night. Took forever, didn't it? Okay, a couple of review concepts that we need to remember is factoring the sum and difference of cubes. Remember our pattern. If I have a cubed plus b cubed, you take the cube root of the first, the same sign, the cube root of the second. Then you have the a plus b, and then you square the first, so we have a squared. Opposite sign, you multiply the two together, so ab, always positive because positive, negative. And then square the last. The difference is the same pattern. Remember doing that? When we wrote it before last year, all we did is wrote the same thing and put a minus down here. Not an erase. A minus down here. And then a minus here. And then a plus here. I wouldn't waste my time rewriting it twice. You guys need to remember factoring sum and difference of cubes. It comes up. It's important. Okay, the next thing you need to remember is conjugates. Remember conjugates, when I multiply them together, I have no middle term. Bless you. Also known as difference of squares. So the conjugate of 3x plus 1 is 3x what? Minus 1. The conjugate of the square root of x plus 2 is the square root of x what? Minus 2. Okay, we're going to have to use those concepts. From time to time, I'll throw them up there, so we just have to remember that they're there. Okay, so let's get into the nitty-gritty of today. We're going to do limits, and we don't want to do a table every time, do we? We don't want to graph it every time. So we're going to have a lot of rules, guys, a lot of rules. Anything that's in a box today is out of your book. So if you're running out of time, see at the top, it says Theorem 1.1. Okay, make sure you have that down, and then you can find which box it is. Does that make sense? Okay, some of them are short like this. Some get really long. So I'll say go finish it at home. Got it? Okay, so let b and c be real numbers and let n be a positive integer. Okay, that's all we have. So it says the limit of b as x approaches c. Well, there's no variable with b, is there? It's just a constant. So the answer is b. If you have the limit of b as x approaches some random constant, the answer is b. No other choice. Now we have the limit of x as x approaches c. Well, it's just, guess what? c. And then lastly, we have the limit of x to the n as x approaches c. Well, we have c to the n. What am I doing? I'm substituting in the constant into the x, correct? So in my example, the limit of x squared as x approaches 2. So what does that tell me I need to do? Which one is that? 1, 2, or 3?
3.
No, it's not 3. It's 2.
Oh,
because we've got n as my, I guess we can say, okay, fine, I'll go with that one. It don't matter. It's one of those two, right? So what am I going to do? Hate.
There's a long one.
Yep, there's a long one next. Okay, so it's going to be 2 squared, which is what?
4.
4. So the limit of x squared as x approaches 2 is 2 squared, which is 4. The next one, the limit of 3 as x approaches 2. Well, 3 is a constant yet. Yes?
Yeah.
What rule is that one?
2. No, 1.
1. Remember, b is a constant, isn't it? X is a variable. So the answer is just what?
3.
3. Because it's not changing. That's that horizontal line. Not changing. Okay. The limit of x?
2.
Why 2? The limit of x as x approaches negative 4 is what?
No, I meant rule 2.
Oh, rule 2, yes. Which is
4.
negative 4. Pretty simple, right?
Yep.
Okay. So now the next one, I'm not going to give you enough time to write it all down, but I want you guys to think before you write. Okay? You can go back and write this when you get home if you want, but I want you to stop and listen to me. Okay? It says the properties of limits. These are properties. These aren't rules, are they? Okay. And it says let this be this and this be this and this be this. We're all good. Now, it gives me f of x, the limit is L. And g of x, the limit is what? K. If I want, it's a scalar. Okay, so I have a b times the function, yes? Mm-hmm. It is BL. Well, L is the limit, correct?
Right.
So if I have a number in front of it, it's just the number times the limit. That's all I'm doing. I find the limit and multiply it by the scalar. Make sense? Mm-hmm. Okay, the next one is the sum and difference. Well, if I have the limit of f of x plus or minus g of x, I find the limit of f, find the limit of g, and then do what with it? Add or subtract it. This is just pieces. Does that make sense what I'm saying? Mm-hmm. So if I have the product of f and g, so I find the limit of f, and I find the limit of g, and then do what with them? Multiply them together. Does that all make sense? You don't have to do it all at one time. Okay? Now if the limit of f of x divided by g of x, I find the limit of the numerator, find the limit of the denominator, and then divide them. But the limit of the denominator can't be what?
0.
Why not?
Undefined.
Because it's undefined. Now if I have a power, if I have a function to a power, I just find the limit of the function and raise it to what?
That power.
That power. This just tells me how I can break it apart. Does that make sense what I'm saying? And I'll show you an example here. But that is, you got at least the theorem written down. If you want a theorem 1.2 properties of limits, if you want to go back. But do you get what I'm saying about really not needing this to be down? Just know that they're there, right? Sometimes writing too much stuff is too much. Okay, you good? Mm-hmm. Okay, so for example, let's find it. Now this one, I have x squared plus 3. Well, I'm pointing at it and I need to write because I'm recording. This right here would be f of x, yes? Mm-hmm. And this right here would be what? G of x, wouldn't it? So we would do this, the limit of 4x squared as x approaches 2 plus the limit of what? 3 as x approaches 2. Okay. Well, 4 is also a scalar, isn't it? Isn't 4 a scalar? You guys know what a scalar is, don't you? If I go back, we won't have it anymore. What's a scalar? Just makes it what? Bigger or smaller. So I take x squared and then I multiply it times 4, right? So what I really have over here is the limit 4 times the limit of x squared as x approaches 2 plus the limit of 3 as x approaches what? 2. Okay? So, well, we learned from I think that's rule 3 on the limit of x squared, right? How do I find it? I just plug in the what? The 2, don't I? So I have 4 times 2 squared plus, and rule 1 told me the limit of 3 as x approaches 2 is what? 3. Okay, so 2 squared is 4. 4 times 4 is?
16.
16 plus 3 is? 19. That's it. Now do you see why I said, well, maybe you want to write them down, maybe you don't? Just broke it up, didn't we? Questions? Okay. Okay. Okay, theorem 1.3, limits of polynomials and rational functions. This limit, this one right here actually goes back to this right here. Okay? So it says if p is a polynomial function and c is a real number, okay, then the limit of p of x equals p of c. So basically plug in the constant, yes? Is that what we've been doing on the last two slides?
Yeah.
Yes. Okay, so if r is a rational function given that r of x equals p of x divided by q of x, okay, q stands for quotient, okay, and c is a real number such that q of c can't equal 0 because the denominator can't equal what? 0. All you do is plug in what?
A constant.
All you do is plug in your constant. All you do is plug in this into r, which is your rational function, which is into your numerator and what?
Yeah.
Denominator. We've already been doing this, haven't we? Okay, so down here it says find the limit. As long as the denominator, as long as the constant doesn't make the denominator 0, you can use this method. Correct? Makes it 0, we have to do something else. So all we are going to do on this one, the limit of x squared plus x plus 2 over x plus 1 is plug in what? What's x approaching? 1. Okay? So we're going to have 1 plus 1 plus 2 equals 1 plus 1. Well, 1 plus 1 plus 2 is 4, yes?
Mm-hmm.
Over 2, so my answer is what? 2. Okay? All of these functions so far are continuous functions. There's no holes in them. That's why we can do this. When we were looking at the pictures or the table yesterday, you had holes. You had lots of errors right at the point, didn't you? Okay? When it has an error at the actual value, then you have to use tables or graphs. But in all reality, not a whole lot of functions have errors. They're not all rational functions, are they? And they're not all square root functions, and they're not all of those. So now, you notice, where did I put my work? Where did I put my
On the bottom.
on my bottom? Is it a lot cleaner to do that?
Uh-huh.
We're going to work down, and there's my answer. Okay? And this is just called direct substitution. That's it. Okay, so we have, again, all that stuff on the top is just stuff. Okay? This rule works if n is odd. Okay? If n is odd, it works every time. Got it? But if n is even, which is the root, yes? Can you take an even root of a negative number? No. So if c is negative, it won't work if n is even. But that's just going to come out. You're going to see it. Okay? You don't have to remember that because you know you can't take it. So it just says the limit of the nth root of x is what? I plugged in what again? C. That's it. Is that any different than the rule I just wrote down for you? No. Is it any different than the rule at the very beginning where it just plugged it in? No. They're writing the rules in all different forms. That's it. Okay. The bottom one. If the limit is a composite function. Okay, remember that's f of g, right? So I put g into f, right? Or if it's g of f of x, you put f into g. This one's a little bit trickier here. The limit of f of g of x as x approaches c is equal to f of the limit of g. So I find the limit of g of x, and then I plug it into what? F of x, and find the limit of that. So I just work my way backward like I would any other composite. And that doesn't make a whole lot of sense until we do it, right? Okay, so I have the limit of f of g of x, where f of x is the square root of x, and g of x is x squared plus 4. So this is missing a parenthesis. You guys notice that? Right here?
Where?
Right there?
It's not going on the... Oh.
Yeah, I did. Okay. So I need to find the limit of g of x first, don't I? Okay. So I'm going to... The limit of x squared plus 4 as x approaches 0. Well, how have I been doing these all day? Plugging in what?
Here's the constant.
The constant, which is
0.
0. So equals 0 plus 4, which is
4.
4. All good?
Yep.
So now I plug that into f. F of 4 is the square root of 4, which is
2.
2. So the limit as x approaches 0 of f of g of x is what?
Equals 2.
Equals 2. We're just going to be plugging in a lot of numbers today, yes?
Mm-hmm.
We need to approach something other than 0. What do you guys want to approach? Something other than 0. 2?
2.
Okay. So the next one we're going to do is the limit of g of f of x as x approaches 2. So what do I need to find the limit of? Which one? F. So the limit of f of x as x approaches 2 is going to be 2. And then what do I plug in for the x? 2 squared minus 10. So 2 squared is
4.
times 2 is
8.
8 minus 10 is
-2.
negative 2. And all I do is plug that into what now? G. Oh, wait. It can't be negative 2. Oh, yeah, it can. Wait a second. Oh, I got a different answer before because of the fact I didn't change it. Never mind. Disregard me. So now I plug that into what? G, right? So I have the cube root of negative 2. Do I know the cube root of negative 2?
No.
Nope. So I'm going to leave it the cube root of negative 2, yes? Mm-hmm. So the limit of g of f of x as x approaches 2 is not
Cube root of -2.
the cube root of negative 2. Now, what happens if I came out with the cube root of negative 8? What's my answer?
2.
Negative 2.
-2.
Because it's negative already.
Okay, but what if it was like, so like let's say like square.
So if it was the square root of negative 2?
No, what if it was
Oh.
the square root of like -4? Would it be 2? Or
No,
would it be -2?
it wouldn't be. Can I take the square root of a negative? No. So it would be undefined, so you would have to go to another method like a table or a graph. Do you get that? If it doesn't work, what we're doing, if we get an undefined answer with what we're doing, we would have to move to a table or a graph.
Undefined meaning as it's negative.
Like if I got a negative even root, or I got
So
0
could it
in
be
my
negative
denominator.
3?
What?
Can it be -3?
Yeah, this is a cube root, so it can be any negative. But if my root was positive, and I was taking the even root of a negative number, that wouldn't work. So I would have to go through other steps. I couldn't find my limit this way. The first way I'm always going to check is this. Is this pretty straightforward and easy to do? Yes. So that's why I'm always going to check that way. If that doesn't work, I have to resort to different methods. And that's what we're going to get to here. Okay, so now, first we're going to do this. This you do need, you have to have these. Well, actually, no, not these. Never mind. I'm thinking derivatives. Look up there, really close.
Sine, tans.
Okay, so the sine of x is the sine of c. The tangent of x is the tangent of c. All you're doing is plugging in what?
Our
constant.
You're plugging in your constant that you're approaching. That's all you're doing. So can you paraphrase that box in some words into a sentence?
yeah.
Okay, so do it quick. I mean, other than writing all 6 down. I think that's redundant, don't you?
So all you have to do is put like sign. There.
All you're doing is substituting in your constant. That is it. So then you have to find. So if my constant like was approaching pi. So here, my constant was pi. Yes?
Yeah.
So I have pi here. Well, what's the sign at pi?
0.
0.
Yeah.
That's it. If you need to dig out your circles, you need to get them dug out. But I'm going to tell you, I don't give you your circles on a test. So do you need to remember those? Get those back working. Yes.
I just have to have a little thought there.
Yep.
I can make it in my head.
Does everyone have their statement paraphrased?
Okay.
No?
I'll just put the examples. I'll figure.
I mean, when you see your examples, you'll be like, oh, okay. Okay, so I have the limit as tangent of x as x approaches 0. I plug in what?
Tan 0.
It's tangent of 0, not tan, please. What is the tangent of 0?
Oh God.
Zero is right here, yes?
Yeah.
What's that point right here?
1.
1, 0, yes? And tangent is y over x. What's
So
the y?
0
So it is
over
it's 0 over 1, so it is 0.
Yeah, I'm gonna have to rephrase.
Okay, so now, oh, remember I have a constant, yes? I plug it into both places, don't I? Okay, so I'm plugging in pi. So the limit of x, cosine of x, as x approaches pi is pi cosine of what? Pi?
Pi.
Okay, so pi is pi, isn't it?
Yeah.
What's the cosine at pi? What's this point over here?
1.
Negative 1. And cosine is x. Yes?
Yeah.
Am I going too quick? Am I going too quick on that?
Can
So-
you re-explain it? Like,
So this point's negative 1, 0, yes?
Yep.
And cosine is x values? So it's negative 1, so pi times negative 1 would be what?
Negative pi.
Negative pi. Do you now know why last year I tortured you on learning those? And I know they're not yet there yet, but as you use them, are they going to come back pretty quickly? You know you can have this, you know you can have this, 30, 60, 90, right? And you can have 45, 45. So if, with those 3 things, should you be able to find anything on a circle?
Yep.
Yep. Okay, next one is the sine. Now this one, we need to think about it as this. It's the limit of the sine of x as x approaches 0 squared. Does everyone see that? How I got that?
Yep.
Okay, so now I just plug in 0 into the in part, right? So I have the sine of 0 squared. What is the sine at 0?
0.
0. So 0 squared is
0.
0. Shelby, so big.
How were we able, I don't know, when you took the whole thing squared instead of just sine?
Because you're doing, remember, from last year, when we had sine squared of x, that was sine of x squared.
Okay.
It's the whole thing squared. You're not squaring sine, you're squaring your answer. Okay? Oops. You're good. Shelby?
Yeah. Yeah.
Okay,
I'm like,
so 1 through 6, and we'll do this one and that's it. We're not gonna go any further today. Theorem 1 through 6 was called direct substitution. That was easy. always do it first.
Okay.
But what happens if it doesn't work?
Then to do
Okay.
this.
So if it doesn't work, we're going to have some things we're going to reduce first. We're going to rationalize. We're going to do anything we have to before we have to make a table. Because tables were not efficient, were they? No. Okay, so what this says right there, it says functions that agree at all but one point. All it says basically is to reduce. I would not write that down. That to me makes no sense. I'm going to read it to you. Let C be a real number and let f of x equal g of x at all for all x not equal c in an open interval containing c. If the limit of g of x as x approaches c exists, then the limit of f of x also exists, and the limit of f of x as x approaches c is equal to the limit of g of x as x approaches c. It says reduce. Got it?
Yes.
If you can reduce, do what?
Reduce.
Reduce. Okay, this is the problem. Direct substitution. Do it. What would I get? What's my
X.
denominator?
0.
0. Can I do it?
No.
No, because my denominator is what?
0.
0. So that doesn't work. So now I need to do what? Reduce. Can you factor the numerator?
Yeah.
It's difference of cubes. That's why I put it up there at the beginning. So difference of cubes says that I'm going to have cube root of the first. So the cube root of x cubed is x, yes? Yes? Same sign. What is the cube root of 1?
1.
1. So now this quantity here is my a and my b, my first and my second. So square x, I get x squared, correct? Opposite sign,
Plus
plus,
1.
multiply the two together. So you get x, yes?
Yeah.
And then plus, always, and square the last. 1 squared is what?
1.
1. All over x minus 1. Can I reduce something?
Yes, the x minus 1.
The x minus 1s. Now, this would be equal to the limit as x approaches 1 of x squared plus x plus 1. Because this theorem up here that had a lot of words says if you reduce, you get the same limit. Yes? Now, I don't have a denominator anymore, so should I be safe?
Yeah.
Yes. So 1 plus 1 plus 1 is
3.
3. What did we do first? We tried what? Did we try direct substitution? That gave me a 0 and the denominator didn't work, correct? So then what did I do? Reduced. Did it work then? Yes. Because this at 1, there is a hole in my graph, isn't there?
Yeah.
Because it can't equal 1. That graph looks like something like that, doesn't it?
Yep.
There's a hole there. And that was that picture of those graphs that you saw. So this is approaching 3 right here. Does that make sense, what I'm saying? Okay, so direct substitution first. If direct substitution fails, you're going to do what? Reduce. Now, I don't know. We've gone kind of quick, and I am posting this, so if you need to rewatch it, can you rewatch it?
Yes.
Yes. Now, let me stop.